Okay, so that's our finance example, right? So now I want to talk about this thing from economics. It's called the elasticity of demand. And what this is elasticity refers to how sensitive the demand is to changes in the price. So let me give you a couple of examples. Um, Cruise ships, cruise lines. Uh, they are a luxury item. They are very sensitive to changes in the price because first, people don't have to buy one. They can choose to just put it off their vacation and not buy it at all. And second, there are lots of alternative products. There are plenty of other vacation options if the cruise price gets too expensive for you, right? On the other kind of end of the elasticity scale would be something like gasoline. It's not perfectly elastic or inelastic, but you have to drive to work. You have to drive to school. Trucking companies, they have to fill up their tank and deliver goods to wherever they've been hired to deliver them. So the demand for gas is relatively resistant to changes in the price. Now, obviously, there are limits, right? People can change their driving habits, right? There are things that people can do to minimize their usage, but it's really hard to stop buying altogether and go to buy something else. All right, so how do we measure this thing? Well, this is based on comparing percentages. Right, I'm going to take the ratio of the change in demand, the percent change. That's this. So it's going to be delta Q divided by Q. And I'm going to divide that by the percent change in the price. That's this. Delta P divided by P. Okay, now, suppose that Q is equal to F of P. In other words, the demand is a function of the price, right? Well, in that case, delta Q is equal to, that's the change, right? The change in the demand is equal to F of P plus delta P. That's the new demand after the price increase, minus F of P. That's the original price. All right, so let's see. I'm going to put that into our formula, but I'm going to fix this fraction up a little. Remember, how do you divide two fractions? You keep the first one the same, so it's going to be delta Q over Q. You change the division to multiplication, and you flip the second one over. So this is P over delta P. Now, again, I'm going to rearrange this a little more. I'm going to put the P and Q together, so that's P over Q. And I'm going to put the deltas together. So that's delta Q over delta P. All right, now let's make my substitution. I'm going to replace that. I'm going to leave the P over Q alone, P over Q. I'm going to replace delta Q with this. So that's F of P plus delta P minus F of P over delta P. Okay, hopefully that second fraction there, hopefully that looks familiar, right? If you replace that delta P with H, because we usually use an H, if you put an H in there instead, that looks an awful lot like that difference quotient that we used all the time back when we were first looking at the derivative. All right, so here's what I'm going to do. I'm going to take the limit as delta P approaches 0 of the whole thing, P over Q, times F of P plus delta P minus F of P over delta P. Now, the P and the Q, they don't, this first fraction, they don't depend on delta P at all. So I'm just going to bring those out in front. This is P over Q times the limit delta P approaches 0, Fp plus delta P minus F of P over delta P, right? And this is what I needed, right? This is where I was trying to go with this. That limit is F prime of P. So this is P over Q times F prime of P. Back up here, my definition, right? F is just the same as Q. That's my demand function. So this is P over, whoops, clean that up. This is, let's try that again, P over Q times Q prime. And let's make it clear, Q prime of P, that is a function of the price. Okay, this is what we want for our elasticity, although the economics guy, they do make one little switch. The way elasticity is defined, elasticity is negative P over Q times Q prime of P. They throw that negative sign out in front. And kind of the reasoning is, look, what does Q prime look like? Q prime is the demand, and we know just from your basic economics class, as the price goes up, the demand goes down. Right? So as the price goes this way, the demand goes this way. That means Q prime is always going to be a negative number. This is a decreasing function. And they kind of like for these elasticity numbers to be positive numbers. Just positive numbers are often just easier to work with. You don't have to worry about an extra negative sign floating around your calculations and whatnot. So that's why that negative number, that minus sign kind of gets thrown in front. Just make sure we're always going to be looking at positive quantities. So at the top here, I've summarized the conclusion of our calculations. Elasticity is equal to these two formulas, and all that's different here is the way I wrote the derivative. Here I use the dq over dp notation. Here I use q prime. Whichever one is clearer to you. I usually use the q prime, but it's the same thing either way. And then down here I've got kind of what these things mean. If the elasticity is less than 1, then that means that revenue increases as price increases. In other words, the product is a necessity. So a change in price has relatively little impact on the demand. Right now, the other way around here, the demand is elastic if E is equal to 1, and that means that revenue decreases as price increases. In other words, the revenue will change. Right? If you change your price, you can expect there to be a change in demand for the worse, right? Revenue is going to decrease, which means people are not buying. This is the case where the product is not a necessity. So let's see how these work. Right, let's do an example. Right, the demand for crude oil in the United States is given by this function here, right? And I want to know what the elasticity is. What's the elasticity of demand when the price specifically is $100 per barrel? All right, well, let's use our formula, right? Elasticity is negative P over Q times Q prime of P. What I want to emphasize to you here is P is the independent variable. P is like the X in this situation. Right, so I'm going to leave that negative P just the way it is. And down here, I'm going to put my formula for Q. There's some weird numbers here. 2431129 P to the negative 0.06. Okay. Now I need the derivative. Well, I know the numbers are big and kind of weird looking, but look. That's just a polynomial. Well, that's not a polynomial because the exponent is negative. But this is P to a power, P to a number. So the power rule applies here. Right? What am I going to do? I'm going to leave the constant out in front the same, 2431129. I'm going to multiply by the exponent, negative 0.06, and I'm going to reduce the exponent by 1. Now you see why I was looking ahead. You see why I didn't try to multiply that out? These big numbers here, they're going to cancel. Right? They're going to cancel. Then what happens? Let's see. The two negative signs, they cancel each other. So I'm left with 0.06 times p to the negative 1.06 divided by p to the negative 0.06. Now, you know how we do exponents, right? You add them all up. Well, you add in the numerator when you're multiplying. So this is a 1. So the final exponent will be 1 plus negative 1.06 minus the exponent that's in the denominator. And if you work these out, this comes out to 0. Right? So this is 0.06 p to the 0 power, which is 0.06. And that's it. That's my elasticity. Right? It turned out to be a constant. And what is the elasticity when p is 100? Well, it's 0.06, right? Because it's a constant. All right, so what does that mean? Well, look, this is less than 1, right? That means this is inelastic. In other words, the product is resistant, the demand is resistant to changes in the price, right? And that's kind of what we expect from oil. Oil is used to make gas and petroleum products and so forth. It's not something that you can easily do without. It's not something for which there are a lot of substitutes, right? So that's good. That's the kind of number that we expected to see for this particular type of product.
In the lectures back in chapter 1, we looked at methods for solving or evaluating limits like these. And you remember the first one involves some kind of unusual algebra manipulations where we had to rationalize the numerator, and on the right-hand one, if I remember right, we had to invoke the squeeze theorem and just do some kind of unusual manipulations. Well, it turns out there's a method, there's a theorem, it's called L'Hopital's rule, that gives us a very quick, very simple way to evaluate limits that look like these two, right? So that's what we're going to be talking about in the next series of lectures.